Hello there. Tonight we are going to explore the most relaxing space facts to help you fall into a deep, restorative sleep. Right now, as you settle into stillness, 93 million miles away from where you lie, a sphere of plasma burns with such patient constancy that it has sustained every breath you've ever taken, every thought you've ever formed, every moment of warmth you've ever felt. And it will continue this silent work long after you drift into the deepest layers of sleep, its light traveling across the void at 186,000 miles per second, reaching Earth in just over 8 minutes, bathing our world in the golden radiation that makes life possible. The Sun is not a solid object, but a sphere of superheated gas, primarily hydrogen and helium, held together by its own gravity. At its core, temperatures reach about 27 million degrees Fahrenheit, hot enough to sustain nuclear fusion, the process by which hydrogen atoms are forced together under immense pressure and temperature to form helium, releasing tremendous amounts of energy in the process. This energy radiates outward from the core, taking hundreds of thousands of years to work its way to the surface, bouncing between atoms, being absorbed and re-emitted countless times, gradually losing energy and shifting to longer wavelengths as it travels. By the time this energy reaches the Sun's surface, the photosphere, it has transformed from high-energy gamma rays into the visible light and infrared radiation that warm our planet. The photosphere itself is relatively cool compared to the core, only about 10,000 degrees Fahrenheit. And it's what we see when we look at the Sun, a brilliant, golden disk that appears solid, but is actually a roiling surface of convection cells, granules of rising hot plasma and sinking cooler plasma, each granule about the size of Texas, constantly churning, constantly renewing, a surface that never rests, never sleeps, never stops its patient work of radiating energy into the cosmos. The Sun rotates, though not as a solid body. Because it's made of plasma, different parts rotate at different speeds. The equator completes a rotation in about 25 days, while the polar regions take about 35 days. This differential rotation creates complex magnetic fields that wind and twist through the Sun's interior and atmosphere, emerging at the surface as sunspots, dark regions that appear dark only because they're slightly cooler than the surrounding photosphere, though they're still incredibly hot, around 6,500 degrees Fahrenheit. These sunspots come and go in an 11-year cycle, waxing and waning in number and intensity, a rhythm that has persisted for billions of years, a cosmic heartbeat that influences space weather, auroras, and even subtle effects on Earth's climate. The magnetic fields associated with sunspots can become twisted and tangled, and when they reconnect, they release enormous amounts of energy in solar flares and coronal mass ejections. Explosions that send billions of tons of plasma hurtling into space at millions of miles per hour. Yet even these violent events are part of the Sun's natural rhythm, part of the cycle that has repeated countless times over the eons, a reminder that even stars have their seasons, their moods, their patterns of activity and rest. Above the photosphere lies the chromosphere, a thin layer of the Sun's atmosphere that's visible during solar eclipses as a reddish glow around the Moon's silhouette. The chromosphere is hotter than the photosphere, reaching temperatures of about 14,000 degrees Fahrenheit, and it's the source of prominences, vast loops and arcs of plasma that follow magnetic field lines, sometimes extending hundreds of thousands of miles into space before falling back to the surface. These prominences can persist for days or weeks, graceful arcs of glowing gas suspended in the Sun's magnetic embrace, visible reminders of the invisible forces that shape the Sun's behavior. Watching time-lapse footage of solar prominences is like watching a slow-motion ballet performed by matter in its most energetic state. Plasma dancing to the choreography of magnetic fields, rising and falling with a grace that belies the violence of the forces involved. Some prominences erupt, breaking free from the sun's gravitational hold and streaming into space, while others collapse back onto the surface, their energy dissipating, their brief moment of prominence ending, as they merge back into the seething plasma of the chromosphere. Beyond the chromosphere lies the corona, the sun's outer atmosphere, a region of extremely hot, tenuous plasma that extends millions of miles into space. The corona is paradoxically much hotter than the layers beneath it, reaching temperatures of 1 to 3 million degrees Fahrenheit, and the mechanism that heats it to such extreme temperatures is still not fully understood, though it's thought to involve magnetic reconnection and wave heating. The corona is visible during total solar eclipses as a pearly white halo around the darkened sun, with streamers and plumes extending outward, tracing the sun's magnetic field lines. The corona is also the source of the solar wind, a continuous stream of charged particles, mostly protons and electrons, that flows outward from the sun at speeds of about 250 to 500 miles per second, filling the solar system with a tenuous plasma that interacts with planetary magnetic fields and atmospheres. This solar wind creates the heliosphere, a vast bubble of solar influence that extends far beyond the orbits of the planets, reaching out to about 100 astronomical units from the Sun, where it finally encounters the interstellar medium, the thin gas that fills the space between stars. The Sun has been shining for about 4.6 billion years, and it will continue to shine for another 5 billion years or so before it exhausts the hydrogen in its core. When that happens, the core will contract and heat up, while the outer layers will expand, transforming the Sun into a red giant that will engulf Mercury, Venus, and possibly Earth. But that transformation is so far in the future that it has no relevance to anything happening now or in the imaginable future. For now, for billions of years to come, the Sun will continue its patient work, fusing hydrogen into helium, radiating energy into space, warming our planet, driving our weather, powering photosynthesis, sustaining the web of life that has evolved under its light. The Sun is the ultimate source of nearly all energy on Earth. Fossil fuels are stored sunlight from millions of years ago. Wind is driven by uneven solar heating. Hydroelectric power comes from water evaporated by the sun and returned as rain. Even the food we eat is ultimately derived from photosynthesis, the process by which plants capture solar energy and convert it into chemical energy. The energy the sun produces is staggering, about 386 billion megawatts, equivalent to exploding 100 billion tons of TNT every second. Yet this represents only a tiny fraction of the sun's mass being converted to energy through Einstein's equation, E·mc². The sun loses about 4 million tons of mass every second through this conversion, but it's so massive, about 333,000 times the mass of Earth, that this loss is negligible, and it will take billions of years before the sun's mass decreases significantly. The sun contains about 99.86% of all the mass in the solar system, dominating gravitationally, holding all the planets, asteroids, and comets in their orbits through the invisible tether of gravity. Without the sun's gravity, the solar system would not exist. The planets would drift apart, wandering through the galaxy as rogue worlds, cold and dark, devoid of the energy that makes life possible. The energy the sun produces is staggering, about 386 billion megawatts, equivalent to exploding 100 billion tons of TNT every second. Yet this represents only a tiny fraction of the Sun's mass being converted to energy through Einstein's equation, E·mc². The Sun loses about 4 million tons of mass every second through this conversion, but it's so massive, about 333,000 times the mass of Earth, that this loss is negligible, and it will take billions of years before the Sun's mass decreases significantly. The Sun contains about 99.86% of all the mass in the solar system, dominating gravitationally, holding all the planets, asteroids, and comets in their orbits through the invisible tether of gravity. Without the Sun's gravity, the solar system would not exist. The planets would drift apart, wandering through the galaxy as rogue worlds, cold and dark, devoid of the energy that makes life possible. The light that reaches Earth from the Sun has traveled for 8 minutes and 20 seconds, crossing the vast emptiness of space at the speed of light. This means that when you look at the Sun, though you should never look directly at it without proper protection, you're seeing it not as it is now, but as it was 8 minutes ago. The Sun could theoretically cease to exist, and we wouldn't know for 8 minutes, wouldn't feel the loss of its warmth, wouldn't see the darkness descending, until that final wavefront of light reached us. This light, this electromagnetic radiation spanning wavelengths from radio waves to gamma rays, carries not just energy, but information. By analyzing sunlight, astronomers can determine the Sun's composition, temperature, rotation rate, and magnetic field structure. The spectrum of sunlight reveals absorption lines, dark bands where specific wavelengths have been absorbed by elements in the Sun's atmosphere, creating a unique fingerprint that identifies the elements present: hydrogen, helium, oxygen, carbon, iron, and dozens of others in trace amounts. The Sun's influence extends far beyond the light and heat we feel on Earth's surface. The solar wind, that continuous stream of charged particles flowing outward from the corona, interacts with Earth's magnetic field, creating the magnetosphere, a protective bubble that shields us from harmful cosmic radiation. When the solar wind is particularly strong, such as during a coronal mass ejection, it can compress the magnetosphere, and particles can leak through near the poles, spiraling down magnetic field lines and colliding with atoms in the upper atmosphere. These collisions excite the atoms, causing them to emit light. This is the aurora, the northern and southern lights, curtains of green, red, and purple light that dance across the polar skies, a visible manifestation of the Sun's influence, a reminder that we live within the Sun's domain, bathed in its radiation, protected by our planet's magnetic field, connected to our star in ways both visible and invisible. The Sun also influences Earth's climate through variations in its output. The 11-year solar cycle, marked by the rise and fall of sunspot numbers, corresponds to small variations in the Sun's total energy output, about 0.1% from solar minimum to solar maximum. While this seems small, it can have measurable effects on Earth's climate, particularly in the upper atmosphere. Longer-term variations, such as the Maunder minimum in the 17th century when sunspots nearly disappeared for several decades, have been correlated with cooler periods on Earth, though the mechanisms are complex and not fully understood. The Sun's output has also increased over its lifetime. When the Sun first formed, it was about 30% dimmer than it is today, and it will continue to brighten slowly as it ages, eventually making Earth too hot for life, long before the Sun becomes a red giant. Leaving the golden warmth of our Sun behind, we drift closer to home, to the celestial companion that has watched over Earth for 4.5 billion years. a silent sentinel that hangs in our sky, pulling at our oceans, stabilizing our axis, lighting our nights with reflected sunlight. The moon is Earth's only natural satellite, a world of ancient craters and vast plains, airless and waterless, yet intimately connected to our planet through the invisible force of gravity, a force so gentle yet so persistent that it shapes the rhythm of our tides, influences the behavior of countless organisms, and has inspired human wonder and mythology since our species first looked up at the night sky. The moon formed about 4.5 billion years ago, shortly after Earth itself, in a cataclysmic collision between the young Earth and a Mars-sized object called Theia. The impact was so violent that it vaporized much of both bodies, sending debris into orbit around Earth. This debris gradually coalesced under its own gravity, forming the moon. This giant impact hypothesis explains many of the moon's characteristics, why it has a relatively small iron core compared to Earth, why its composition is similar to Earth's mantle, why it's so large relative to its parent planet. The moon is about 1/4 the diameter of Earth, making the Earth-Moon system almost a double planet rather than a planet and satellite. This large size relative to Earth has profound effects on our planet's stability and habitability. The collision that created the moon also tilted Earth's axis and may have contributed to the formation of Earth's magnetic field by stirring the molten iron in Earth's core, creating the dynamo that generates the protective magnetic bubble surrounding our planet. The moon's surface is covered with craters, the scars of billions of years of impacts from asteroids and comets. The largest of these craters, visible even to the naked eye, are filled with dark volcanic rock, creating the features we call maria, Latin for seas, though they contain no water. These maria formed billions of years ago, when the moon was still geologically active, when impacts fractured the crust and allowed molten rock from the interior to flow out and fill the basins. The lighter-colored regions, the highlands, are older, more heavily cratered terrain, representing the moon's original crust. The moon has been geologically dead for billions of years, with no volcanism, no plate tectonics, no erosion from wind or water. The footprints left by Apollo astronauts in 1969 are still there, perfectly preserved, and will remain for millions of years, slowly degraded only by micrometeorite impacts and the effects of solar radiation. The lunar regolith, the layer of dust and broken rock covering the surface, has accumulated over billions of years from meteorite impacts, creating a layer several meters thick in some places, a record of the solar system's violent history written in pulverized stone. The moon is tidally locked to Earth, meaning it rotates on its axis at the same rate it orbits Earth. So the same side always faces us. This synchronous rotation is the result of tidal forces. Earth's gravity has raised tidal bulges on the moon, and the friction from these bulges has gradually slowed the moon's rotation until it became locked. This is why we always see the same face of the moon, why there's a far side that remained unknown until spacecraft photographed it in 1959. The far side is quite different from the near side, with fewer maria and more heavily cratered highlands, possibly because the crust is thicker on the far side, making it harder for lava to reach the surface. The far side also experiences the same day-night cycle as the near side, contrary to the common misconception of a dark side. All parts of the moon receive sunlight during the lunar day, which lasts about 2 Earth weeks. The moon orbits Earth at an average distance of about 238,855 miles, though this distance varies because the orbit is elliptical, not circular. At perigee, the closest approach, the Moon is about 225,623 miles away. At apogee, the farthest point, it's about 252,088 miles away. This variation in distance affects how large the Moon appears in our sky and is responsible for the difference between total and annular solar eclipses. When the Moon is at perigee during a new moon, it appears large enough to completely cover the Sun, creating a total solar eclipse. When it's at apogee, it appears slightly smaller and doesn't quite cover the Sun, leaving a ring of sunlight visible around the Moon's silhouette. This is an annular eclipse. The Moon's apparent size in our sky is almost exactly the same as the Sun's apparent size, a cosmic coincidence that makes total solar eclipses possible and spectacular, with the Sun's corona visible as a pearly halo around the darkened disk of the Moon. The Moon's gravity pulls on Earth, and Earth's gravity pulls on the Moon. But because Earth is much more massive, the Moon's effect is more noticeable. The Moon's gravity creates tidal bulges in Earth's oceans, pulling the water toward the Moon on the side facing it, and creating a corresponding bulge on the opposite side due to inertial effects. As Earth rotates beneath these bulges, different locations experience high and low tides. Most coastal areas experience 2 high tides and 2 low tides each day, separated by about 6 hours. The Sun also contributes to tides, and when the Sun and Moon align during new and full moons, their gravitational effects combine to create spring tides, which are higher than average. When the Sun and Moon are at right angles during quarter moons, their effects partially cancel, creating neap tides, which are lower than average. These tidal rhythms have influenced the evolution of coastal ecosystems, with many organisms timing their reproductive cycles, feeding behaviors, and migrations to the tides. Tidal forces don't just affect the oceans, they also affect the solid Earth, raising tidal bulges in the crust itself, though these are much smaller than ocean tides, only about a foot in height. The friction from these tidal bulges is gradually slowing Earth's rotation, making days longer. About 620 million years ago, a day was only about 22 hours long. The day is currently lengthening by about 1.7 milliseconds per century, a tiny amount, but measurable with atomic clocks. At the same time, the Moon is gradually moving away from Earth, receding at about 1.5 inches per year. This happens because the tidal bulges on Earth are carried ahead of the Moon by Earth's rotation, and the gravitational pull of these bulges accelerates the Moon in its orbit, causing it to spiral outward. Eventually, billions of years from now, the Moon will be so far away that it will no longer appear large enough to create total solar eclipses, and Earth's rotation will have slowed so much that a day will equal a month, with Earth and Moon both tidally locked, always showing the same face to each other. The Moon has no atmosphere, no air to scatter sunlight, so the sky is always black, even during the lunar day. Without an atmosphere, there's no weather, no wind, no sound. The Moon is a world of absolute silence. Temperatures vary wildly between lunar day and night because there's no atmosphere to moderate them. During the lunar day, which lasts about 2 Earth weeks, temperatures at the equator can reach 260 degrees Fahrenheit. During the lunar night, also about 2 Earth weeks long, temperatures can drop to minus 280 degrees Fahrenheit. This extreme temperature range makes the Moon a harsh environment, though permanently shadowed craters near the poles, which never receive sunlight, are even colder, cold enough that water ice can persist for billions of years. Recent missions have confirmed the presence of water ice in these permanently shadowed regions, a discovery that could be important for future lunar exploration, as water can be used for drinking, growing food, and producing rocket fuel. The moon's influence on Earth extends beyond tides. The moon stabilizes Earth's axial tilt, which is currently about 23.5 degrees. Without the moon, Earth's tilt would vary chaotically over millions of years due to gravitational perturbations from other planets, potentially swinging from nearly 0 degrees to 85 degrees. Such variations would cause extreme climate changes, making it difficult for complex life to evolve. The moon's stabilizing influence has kept Earth's tilt relatively constant, maintaining stable seasons and a relatively stable climate over the billions of years it took for life to evolve from simple cells to complex organisms. This stability may be one reason why Earth has been able to support complex life, while other planets in our solar system have not. The moon has been a source of wonder and inspiration throughout human history. Ancient cultures tracked the moon's phases, using them to measure time and create calendars. The lunar cycle from new moon to new moon is about 29.5 days, and many cultures based their calendars on this cycle. The moon has been associated with fertility, madness, transformation, and mystery in countless mythologies. The word month derives from moon, and many languages retain this connection. The moon's phases, waxing crescent, first quarter waxing gibbous, full moon waning gibbous, last quarter waning crescent, have been observed and recorded for millennia, their regular progression a reliable marker of time's passage. The Apollo missions between 1969 and 1972 brought 12 humans to the moon's surface, the only celestial body beyond Earth that humans have visited. These astronauts walked on the lunar surface, collected samples, conducted experiments, and looked back at Earth hanging in the black lunar sky, a blue and white marble, fragile and beautiful. The moon rocks they brought back have provided invaluable information about the moon's formation, composition, and history. Analysis of these rocks confirmed that the moon is about 4.5 billion years old, that it formed from debris created by a giant impact, and that it was once geologically active, with volcanism continuing until about 1 billion years ago. The Apollo missions also left behind scientific instruments, including seismometers, that detected moonquakes, revealing that the moon has a small core and is still slightly geologically active, though far less so than Earth. Drifting farther from Earth and Moon, we cross the orbital path of our neighboring world, the fourth planet from the Sun, a rusty sphere of ancient deserts and towering volcanoes, a world that once may have harbored rivers and lakes, perhaps even life, but now lies cold and dry, its thin atmosphere unable to retain warmth or liquid water on its surface. Mars has captivated human imagination for centuries, appearing as a reddish star in our night sky, named for the Roman god of war, inspiring countless stories of Martian civilizations, and now the target of robotic explorers and future human missions. Tonight, we explore the red desert, the ancient solitude of Mars, and discover that this world, though seemingly barren, holds clues to the history of our solar system and perhaps to the question of whether life exists beyond Earth. Mars is about half the diameter of Earth and has only about 1/10 Earth's mass, making it a smaller, less massive world with weaker gravity, about 38% of Earth's surface gravity. If you weigh 100 pounds on Earth, you would weigh only 38 pounds on Mars, and you could jump nearly 3 times as high. This lower gravity has allowed Mars to retain a thinner atmosphere than Earth, though it once had a thicker atmosphere billions of years ago. The current Martian atmosphere is about 100 times thinner than Earth's, composed mostly of carbon dioxide, with traces of nitrogen and argon. This thin atmosphere provides little protection from solar radiation and cosmic rays, and it's too thin to retain heat, so surface temperatures vary wildly. From about 70 degrees Fahrenheit near the equator during summer days to minus 225 degrees Fahrenheit at the poles during winter nights. The red color of Mars comes from iron oxide, rust, covering much of its surface. Billions of years ago, when Mars had liquid water on its surface, iron in the rocks reacted with oxygen in the atmosphere and water, forming iron oxide that gives the planet its distinctive rusty hue. This oxidation process has colored the dust that covers much of the Martian surface, and when winds lift this dust into the atmosphere, it can create planet-wide dust storms that obscure the surface for weeks or months. These dust storms are most common during Martian spring and summer in the southern hemisphere, when Mars is closest to the Sun and solar heating is strongest. The dust suspended in the atmosphere gives the Martian sky a butterscotch color during the day, quite different from Earth's blue sky. And during dust storms, the sky can turn dark orange or brown, blocking sunlight and causing temperatures to drop. Mars experiences seasons much like Earth because its axis is tilted at about 25 degrees, similar to Earth's 23.5-degree tilt. However, Martian seasons are nearly twice as long as Earth's, because Mars takes about 687 Earth days to complete one orbit around the Sun. The seasons are also more extreme in the southern hemisphere, because Mars's elliptical orbit brings it closer to the Sun during southern summer and farther away during southern winter. This difference in solar heating drives the massive dust storms that can engulf the entire planet. During winter, at each pole, temperatures drop so low that carbon dioxide from the atmosphere freezes out, forming a seasonal cap of dry ice that can extend thousands of miles from the pole. In spring, this dry ice sublimes back into the atmosphere, creating winds and sometimes triggering dust storms. As the seasonal cap retreats, Mars has some of the most spectacular geological features in the solar system. Olympus Mons is the largest volcano in the solar system, rising about 13.6 miles above the surrounding plains, nearly 3 times the height of Mount Everest, and spanning about 370 miles across its base, roughly the size of Arizona. Olympus Mons is a shield volcano similar to the volcanoes in Hawaii, but vastly larger, built up over millions of years by repeated lava flows. The volcano is so large that if you stood on its summit, the slopes would extend beyond the horizon in all directions, and you wouldn't be able to see the base. Olympus Mons is thought to be extinct, with no volcanic activity for hundreds of millions of years, though it's difficult to be certain since Mars has no plate tectonics to recycle its crust, and volcanic features can persist for billions of years. Valles Marineris is a vast canyon system stretching about 2,500 miles across the Martian equator, roughly 1/4 of the planet's circumference. It's about 4 miles deep in places and up to 120 miles wide, dwarfing Earth's Grand Canyon. Valles Marineris was not carved by water erosion like the Grand Canyon, but formed through tectonic activity, probably related to the formation of the Tharsis volcanic region to the west. The canyon walls show layered rock formations that provide a record of Martian geological history, and some areas show evidence of past water flow, with channels and deposits that suggest water once flowed through parts of the canyon system. Evidence for past water on Mars is abundant. Orbital images show networks of valleys that look like dried-up river systems, deltas where rivers once emptied into lakes or seas, and layered sedimentary rocks that form in the presence of water. Rovers on the Martian surface have found rounded pebbles that were shaped by flowing water, minerals that form only in the presence of water, and mudstone formed from ancient lake beds. All this evidence points to a warmer, wetter Mars billions of years ago, a world with rivers, lakes, and perhaps even an ocean covering much of the northern hemisphere. This ancient Mars would have been more hospitable to life, with liquid water, a thicker atmosphere, and a warmer climate, though it's unclear how long these conditions persisted. The polar ice caps of Mars are permanent features, composed of water ice covered by seasonal layers of frozen carbon dioxide. The northern ice cap is larger and contains enough water ice that if it melted, it would cover the entire planet in a layer of water, about 35 feet deep. The southern ice cap is smaller and sits atop a plateau, elevated above the surrounding terrain. Both caps show beautiful spiral patterns created by winds and the Coriolis effect as the ice accumulates and erodes over time. Beneath the polar ice, radar measurements have detected what appears to be liquid water, possibly kept liquid by dissolved salts, that lower the freezing point, though this interpretation remains debated among scientists. What happened to Mars's water and atmosphere? Much of it was lost to space. Mars has no global magnetic field like Earth's, which protects our atmosphere from being stripped away by the solar wind. Without this protection, the solar wind gradually eroded Mars's atmosphere over billions of years, and as the atmosphere thinned, the climate cooled, and liquid water could no longer exist on the surface. Some water froze into the polar ice caps, which contain both water ice and frozen carbon dioxide, and some water may have soaked into the ground, forming subsurface ice deposits. Recent discoveries suggest that liquid water may still exist in subsurface aquifers, or as briny flows that appear seasonally on steep slopes, though this remains controversial and requires further investigation. Mars has two small moons, Phobos and Deimos, both irregularly shaped and heavily cratered, probably asteroids captured by Mars's gravity early in the solar system's history. Phobos, the larger of the two, is only about 14 miles across and orbits Mars at a distance of only 3,700 miles, closer than any other moon in the solar system orbits its planet. Phobos orbits Mars 3 times per Martian day, rising in the west and setting in the east, and it's gradually spiraling inward due to tidal forces, destined to either crash into Mars or be torn apart by tidal stresses in about 50 million years. Deimos is smaller, about 7.5 miles across, and orbits farther out, taking about 30 hours to complete one orbit. Both moons are dark, reflecting only about 6% of the sunlight that strikes them, and they're thought to be composed of carbon-rich rock, similar to certain types of asteroids. Mars has been explored by more spacecraft than any other planet except Earth. Dozens of missions have been sent to Mars since the 1960s, though many have failed. Mars has a reputation for being difficult to reach, with about half of all missions failing due to technical problems or accidents. Successful missions have included orbiters that have mapped the planet in exquisite detail, landers that have analyzed the soil and atmosphere, and rovers that have explored the surface, traveling miles across the Martian landscape, climbing hills, drilling into rocks, and searching for signs of past life. The Viking landers in the 1970s were the first to successfully land on Mars and conduct experiments searching for life, though the results were inconclusive. More recent rovers, including Spirit, Opportunity, Curiosity, and Perseverance, have found compelling evidence that Mars once had conditions suitable for life, with liquid water, organic molecules, and energy sources that could have supported microbial life. The Perseverance rover, which landed in Jezero crater in 2021, is currently collecting samples of Martian rock and soil that will eventually be returned to Earth by future missions. These samples will be analyzed in laboratories with instruments far more sophisticated than anything that can be sent to Mars, potentially revealing definitive evidence of past life, or at least providing detailed information about Mars's geological and climatic history. Jezero crater was chosen because it once contained a lake fed by a river, and the delta deposits where the river emptied into the lake are excellent places to search for preserved organic material and potential biosignatures. The search for life on Mars continues. While no definitive evidence of past or present life has been found, the possibility remains tantalizing. Mars once had conditions similar to early Earth when life first emerged on our planet, and if life arose on Mars, it might have left fossils or chemical signatures that could be detected. Current missions are searching for these biosignatures, and future missions plan to return samples from Mars to Earth for detailed analysis in laboratories. The question of whether life ever existed on Mars is one of the most profound in science, with implications for understanding the origin and distribution of life in the universe. Mars is also the most likely destination for future human exploration beyond the Moon. While the challenges are immense, the journey takes 6 to 9 months each way. The radiation exposure is significant. The thin atmosphere makes landing difficult, and the cold, dry environment is hostile to human life. Mars is close enough and similar enough to Earth that human missions are conceivable with current or near-future technology. Plans for human missions to Mars are being developed by space agencies and private companies, with timelines ranging from the 2030s to the 2050s. These missions would represent humanity's first steps toward becoming a multiplanetary species, establishing a permanent human presence beyond Earth, beyond the rocky inner planets, beyond the asteroid belt where millions of fragments orbit in the space between Mars and Jupiter. We enter the realm of the gas giants, worlds so massive and so different from Earth that they challenge our understanding of what a planet can be. These are not solid worlds with surfaces you could stand on, but vast spheres of hydrogen and helium, with atmospheres thousands of miles deep, crushing pressures in their interiors, and storms that have raged for centuries. Tonight we drift into the domain of Jupiter and Saturn, the largest planets in our solar system, and discover that these giant worlds are not just massive but beautiful, with swirling clouds, intricate ring systems, and families of moons that are worlds unto themselves. Jupiter is the largest planet in the solar system, more massive than all the other planets combined. It's so large that 1,300 Earths could fit inside it, and it's so massive that it contains about 318 times Earth's mass. Jupiter is composed mostly of hydrogen and helium, the same elements that make up the Sun, and if it had been about 80 times more massive, it would have ignited nuclear fusion in its core and become a star rather than a planet. Jupiter's immense gravity has shaped the solar system, influencing the orbits of asteroids and comets, protecting the inner planets from some impacts by capturing or deflecting objects that venture too close, and creating a family of at least 95 known moons, 4 of which are large enough to be considered worlds in their own right. Jupiter's atmosphere is a dynamic, turbulent place, with winds reaching speeds of 400 miles per hour, clouds of ammonia ice, and other compounds arranged in colorful bands parallel to the equator, and storms that dwarf anything on Earth. The most famous of these storms is the Great Red Spot, an anticyclonic storm that has been raging for at least 350 years. since it was first observed by astronomers in the 1600s. The Great Red Spot is so large that 2 or 3 Earths could fit inside it, though it has been shrinking in recent decades and is now about half the size it was a century ago. The storm rotates counterclockwise, completing 1 rotation every 6 days, with wind speeds at its edges reaching 270 miles per hour. The red color is thought to come from complex organic molecules created by ultraviolet radiation acting on chemicals in Jupiter's atmosphere, though the exact composition remains uncertain. Jupiter's atmosphere is organized into bands of different colors and wind speeds. The light-colored bands, called zones, are regions of rising gas, where ammonia ice condenses into clouds, creating the bright appearance. The dark bands, called belts, are regions of descending gas, where the clouds are deeper and warmer, revealing darker material below. The boundaries between zones and belts are regions of strong wind shear, where winds blow in opposite directions, creating turbulence and smaller storms. These atmospheric patterns are driven by Jupiter's rapid rotation. The planet spins once every 10 hours, the fastest rotation of any planet in the solar system, creating strong Coriolis forces that organize the winds into these east-west bands. Beneath the visible cloud tops, Jupiter's atmosphere becomes denser and hotter with depth. About 600 miles down, the pressure is so great that hydrogen transitions from a gas to a liquid. Deeper still, about 12,000 miles down, the pressure is so immense that hydrogen becomes metallic, a strange state of matter where hydrogen atoms are squeezed so tightly that their electrons can move freely, making the hydrogen conduct electricity like a metal. This metallic hydrogen layer extends most of the way to Jupiter's core and is thought to be the source of Jupiter's powerful magnetic field, the strongest of any planet in the solar system. Jupiter's magnetic field is about 20,000 times stronger than Earth's, creating a magnetosphere that extends millions of miles into space, trapping charged particles and creating intense radiation belts that would be lethal to unprotected humans. At Jupiter's center lies a core, probably composed of rock and ice, with a mass about 10 to 20 times that of Earth. The core is under immense pressure and temperature, perhaps 50,000 degrees Fahrenheit, hotter than the surface of the Sun, though the core doesn't generate energy through fusion like the Sun does. Instead, Jupiter radiates more heat than it receives from the Sun, about 1.6 times as much. Heat left over from the planet's formation 4.6 billion years ago, when gravitational contraction heated the interior, and heat generated by the slow contraction that continues today as Jupiter gradually cools and shrinks. Jupiter's 4 largest moons, discovered by Galileo in 1610, are called the Galilean moons, Io, Europa, Ganymede, and Callisto. Each is a unique world. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes spewing sulfur and sulfur dioxide, creating a constantly changing surface with no impact craters because volcanic activity erases them as quickly as they form. Io's volcanism is driven by tidal heating. Jupiter's immense gravity, along with gravitational tugs from Europa and Ganymede, flexes Io's interior, generating heat through friction. Europa is covered by a smooth ice shell, beneath which lies a global ocean of liquid water, perhaps 60 miles deep, containing more water than all of Earth's oceans combined. This subsurface ocean is kept liquid by tidal heating, and it's one of the most promising places in the solar system to search for life beyond Earth. Ganymede is the largest moon in the solar system, larger than the planet Mercury, and it has its own magnetic field. the only moon known to have one. Callisto is heavily cratered, an ancient surface that has changed little in billions of years, and it too may harbor a subsurface ocean beneath its icy crust. Saturn, the second largest planet in the solar system, is perhaps the most beautiful, with its spectacular ring system visible even through small telescopes. Saturn is similar to Jupiter in composition, mostly hydrogen and helium, but it's less massive and less dense. In fact, Saturn is the least dense planet in the solar system, with an average density less than water, meaning that if you could find an ocean large enough, Saturn would float. Like Jupiter, Saturn has a dynamic atmosphere, with bands of clouds and storms, though they're less prominent and less colorful than Jupiter's. Saturn's winds are even faster than Jupiter's, reaching speeds of 1,100 miles per hour near the equator, the fastest winds in the solar system. Saturn's most distinctive feature is its ring system, a vast, thin disk of ice particles and rock fragments orbiting the planet. The rings extend from about 4,000 miles to about 50,000 miles above Saturn's equator, but they're remarkably thin, only about 30 feet thick in most places. The particles in the rings range in size from tiny grains to house-sized boulders, and they're composed mostly of water ice, which gives them their bright, reflective appearance. The rings are divided into several main sections, separated by gaps where gravitational resonances with Saturn's moons have cleared out particles. The most prominent gap is the Cassini division, a 3,000-mile-wide gap between the A and B rings, visible even through small telescopes. The origin of Saturn's rings is still debated. They may be remnants of a moon that was destroyed by a collision or torn apart by tidal forces, or they may be leftover material from Saturn's formation that never coalesced into a moon. The rings are probably not permanent features. They're gradually being eroded by micrometeorite impacts and by particles spiraling into Saturn's atmosphere, and they may disappear entirely in 100 million years or so. This means we're fortunate to live at a time when Saturn has rings, a temporary adornment that makes the planet one of the most visually stunning objects in the solar system. Saturn has at least 146 known moons, more than any other planet, ranging from tiny moonlets embedded in the rings to Titan, the second largest moon in the solar system. Titan is larger than the planet Mercury and is the only moon with a thick atmosphere, composed mostly of nitrogen, with traces of methane and other organic compounds. Titan's atmosphere is so thick that the surface pressure is about 1.5 times Earth's sea level pressure, and the atmosphere is so hazy that the surface is hidden from view in visible light. Titan's surface features lakes and seas of liquid methane and ethane, rivers that flow with liquid hydrocarbons, and a weather cycle similar to Earth's water cycle, but with methane instead of water. Titan is another promising place to search for life, though any life there would be very different from Earth life, adapted to the cold temperatures of -290 degrees Fahrenheit, and using liquid methane instead of water as a solvent. Enceladus, another of Saturn's moons, is a small, icy world only about 310 miles in diameter, but it has geysers near its south pole that spray water ice and organic molecules into space. These geysers indicate that Enceladus has a subsurface ocean of liquid water beneath its icy crust, kept liquid by tidal heating from Saturn's gravity. The Cassini spacecraft flew through these geysers and analyzed their composition, finding water, salts, and organic molecules, all ingredients necessary for life. Enceladus is now considered one of the best places in the solar system to search for life beyond Earth. Venturing farther from the Sun's warmth, beyond the orbits of Jupiter and Saturn, we enter the twilight realm of the outer solar system, where sunlight is faint and temperatures plunge to hundreds of degrees below zero. Here orbit the ice giants Uranus and Neptune, worlds so distant that they were unknown to ancient astronomers, discovered only after the invention of the telescope. Worlds of methane clouds and icy interiors, tilted axes and dynamic atmospheres. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies left over from the solar system's formation, a frozen archive of primordial material that has remained largely unchanged for 4.6 billion years. Tonight we drift to the edge of the void, exploring these distant worlds and the icy frontier beyond, and discover that even at the solar system's edge, there is beauty, complexity, and mystery. Uranus is the seventh planet from the Sun, orbiting at an average distance of about 1.8 billion miles, so far that sunlight takes about 2 hours and 40 minutes to reach it. At this distance, the Sun appears as a bright star rather than a disk, and it provides only about 1/400th the light and heat that Earth receives. Uranus is about 4 times the diameter of Earth and about 15 times as massive, making it much smaller than Jupiter and Saturn, but still a giant compared to the rocky inner planets. Uranus is called an ice giant rather than a gas giant, because while it has a thick atmosphere of hydrogen and helium, its interior is thought to be composed mostly of water, methane, and ammonia ices under high pressure and temperature, creating exotic states of matter that don't exist on Earth. The most distinctive feature of Uranus is its extreme axial tilt. The planet is tilted 98 degrees relative to its orbital plane, meaning it essentially rolls around the Sun on its side. This extreme tilt means that Uranus experiences the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness, as the planet completes its 84-year orbit around the Sun. The cause of this extreme tilt is thought to be a collision with an Earth-sized object early in the solar system's history, an impact so violent that it knocked the planet onto its side. This collision may also have created Uranus's ring system and some of its moons from the debris. Uranus's atmosphere is relatively featureless compared to Jupiter and Saturn, appearing as a pale blue-green disk with few visible clouds or storms. The blue-green color comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green light. The atmosphere is cold, with temperatures at the cloud tops reaching about -370 degrees Fahrenheit, making Uranus the coldest planet in the solar system, even colder than Neptune despite being closer to the Sun. This is because Uranus radiates very little internal heat, unlike the other giant planets, which all radiate more heat than they receive from the Sun. The reason for Uranus's lack of internal heat is unknown, though it may be related to the collision that tilted the planet, which could have disrupted heat flow from the interior. Despite its generally calm appearance, Uranus does have weather. Observations with powerful telescopes and spacecraft have revealed clouds and storms in the atmosphere, particularly near the poles during their summer seasons, when they receive continuous sunlight. Winds on Uranus can reach speeds of 560 miles per hour, and the planet rotates relatively quickly, completing one rotation in about 17 hours. Uranus has a magnetic field, but it's unusual. The magnetic axis is tilted 59 degrees relative to the rotation axis and is offset from the planet's center, creating a complex asymmetric magnetosphere that tumbles as the planet rotates. Uranus has a system of 13 known rings, much fainter and darker than Saturn's rings, composed of dark particles that may be organic compounds processed by radiation. The rings were discovered in 1977, when Uranus passed in front of a star, and the star's light dimmed briefly several times before and after the planet blocked it, revealing the presence of rings. Uranus also has at least 27 known moons, named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are icy worlds with diverse geological features. Miranda, the smallest of the 5, has one of the most bizarre surfaces in the solar system, with regions of different ages and terrains jumbled together, including a cliff about 12 miles high, suggesting a violent history of impacts and geological activity. Neptune, the 8th and outermost planet, orbits at an average distance of about 2.8 billion miles from the Sun, so far that sunlight takes more than 4 hours to reach it and provides only about 1/900th the light and heat that Earth receives. Neptune is slightly smaller than Uranus, but more massive, about 17 times Earth's mass, and it has a similar composition, with a thick atmosphere of hydrogen and helium surrounding an interior of water, methane, and ammonia ices. Unlike Uranus, Neptune radiates about 2.6 times as much heat as it receives from the Sun. Heat left over from its formation and generated by ongoing gravitational contraction. Neptune's atmosphere is much more dynamic than Uranus's, with prominent cloud features and the fastest winds in the solar system, reaching speeds of 200 miles per hour, faster even than Saturn's winds. The planet appears as a deep blue color, more vivid than Uranus's pale blue-green, also due to methane in the atmosphere, but perhaps enhanced by an unknown component that gives Neptune its richer color. When Voyager 2 flew by Neptune in 1989, it observed a large storm system called the Great Dark Spot, similar to Jupiter's Great Red Spot, but not as long-lived. When the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had disappeared, though other storms have appeared since. Neptune has a ring system, fainter even than Uranus's rings, and at least 16 known moons. The largest moon, Triton, is one of the most interesting objects in the solar system. Triton is the 7th largest moon in the solar system, and is the only large moon that orbits in the opposite direction to its planet's rotation, a retrograde orbit that indicates Triton was captured by Neptune's gravity rather than forming in orbit around the planet. Triton is probably a Kuiper Belt object, similar to Pluto, that wandered too close to Neptune and was captured billions of years ago. Triton has a thin atmosphere of nitrogen and methane, and its surface is covered with nitrogen ice, with temperatures reaching -391 degrees Fahrenheit, the coldest surface temperature measured anywhere in the solar system. Despite the extreme cold, Triton is geologically active. Voyager 2 observed geysers erupting from Triton's surface, spraying nitrogen gas and dark particles several miles into the thin atmosphere. These geysers are thought to be driven by solar heating of subsurface nitrogen ice, which vaporizes and erupts through cracks in the surface ice. Triton's retrograde orbit means it's gradually spiraling inward toward Neptune, and in about 3.6 billion years, it will either crash into Neptune or be torn apart by tidal forces, creating a spectacular ring system around the planet. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies extending from about 30 astronomical units from the Sun, just beyond Neptune's orbit, to about 50 astronomical units. The Kuiper Belt is similar to the asteroid belt, but much larger and more massive, containing hundreds of thousands of objects larger than 60 miles across, and trillions of smaller objects. These are remnants from the solar system's formation, icy planetesimals that never coalesced into a planet, preserved in deep freeze for 4.6 billion years. The Kuiper Belt is the source of short-period comets, those with orbital periods less than 200 years, which are occasionally perturbed into the inner solar system, where they develop tails as solar heating vaporizes their ices. The most famous Kuiper Belt object is Pluto, once considered the 9th planet, but reclassified as a dwarf planet in 2006, when astronomers realized that the Kuiper Belt contains many objects similar in size to Pluto. Pluto orbits at an average distance of about 3.7 billion miles from the Sun, taking 248 years to complete one orbit. Pluto has 5 known moons, the largest of which, Charon, is about half Pluto's diameter, making the Pluto-Charon system almost a double planet. The New Horizons spacecraft flew by Pluto in 2015, revealing a complex, geologically active world with mountains of water ice, plains of nitrogen ice, and a thin atmosphere of nitrogen, methane, and carbon monoxide. Pluto's surface shows evidence of recent geological activity, with some regions appearing to be less than 100 million years old, suggesting that internal heat, perhaps from radioactive decay or tidal interactions with Charon, is still driving geological processes. Leaving the familiar confines of our solar system behind, we venture into the vast spaces between stars, into regions where new stars are born from clouds of gas and dust, where the raw materials of creation gather and collapse under their own gravity, igniting nuclear fusion and illuminating the darkness with newborn light. These stellar nurseries, called nebulae, are among the most beautiful objects in the universe, glowing with the light of young stars, sculpted by stellar winds and radiation into intricate shapes that span light years. Tonight, we explore how stars breathe life into nebulae, how matter transforms from diffuse clouds into blazing suns, and discover that star formation is not just a process of creation, but a cycle that has repeated countless times over billions of years, recycling matter through generations of stars. Nebulae are vast clouds of gas and dust floating in interstellar space, composed primarily of hydrogen, the most abundant element in the universe, along with helium and traces of heavier elements. These clouds can span hundreds of light years and contain enough material to form thousands or even millions of stars. Most of the time, nebulae are cold and dark, with temperatures only a few degrees above absolute zero, and densities so low that they would be considered a vacuum by Earth standards, with only a few hundred atoms per cubic centimeter, compared to trillions of trillions in Earth's atmosphere. But despite their tenuousness, these clouds contain immense amounts of matter, and when conditions are right, they can collapse under their own gravity, fragmenting into smaller clumps that become the seeds of new stars. The process of star formation begins when something disturbs a nebula, compressing part of it and triggering gravitational collapse. This disturbance might be a shockwave from a nearby supernova explosion, the collision of two clouds, the gravitational influence of a passing star, or even the spiral density waves that sweep through galaxies, compressing gas as they pass. Once a region of the cloud becomes dense enough, gravity takes over, pulling more material inward and creating a dense core. As the core contracts, it heats up, converting gravitational potential energy into thermal energy. The temperature and pressure at the center rise, and the core begins to glow, first in infrared light invisible to human eyes, then eventually in visible light as it becomes hotter. This collapsing core is called a protostar, a star in the process of forming but not yet hot enough to sustain nuclear fusion. The protostar continues to accrete material from the surrounding cloud, growing more massive and hotter. Material falling onto the protostar releases energy, heating the surrounding region and creating winds that blow away some of the infalling material. The protostar is often surrounded by a rotating disk of gas and dust, called a protoplanetary disk, from which planets may eventually form. These disks can be hundreds of astronomical units across, containing enough material to form multiple planets, and they're sites of complex chemistry, where simple molecules combine to form more complex organic compounds, the building blocks of life. Jets of material are ejected from the poles of the protostar, perpendicular to the disk, streaming outward at high speeds and creating shock waves where they collide with the surrounding cloud. These jets, called Herbig-Haro objects, when they create visible shock waves, can extend for light years and are driven by magnetic fields that channel material from the inner disk and launch it outward at speeds of hundreds of miles per second. The jets help regulate the star formation process by carrying away angular momentum, allowing more material to fall onto the protostar, and by clearing away the surrounding gas, eventually revealing the newborn star. After hundreds of thousands to millions of years, depending on the protostar's mass, the core becomes hot enough and dense enough for nuclear fusion to begin. Hydrogen atoms are forced together by the immense pressure and temperature, fusing to form helium and releasing tremendous amounts of energy in the process. This energy creates an outward pressure that balances the inward pull of gravity, and the protostar becomes a true star, entering the main sequence phase of its life, where it will remain for millions to billions of years, steadily fusing hydrogen into helium in its core. The transition from protostar to main sequence star is marked by a dramatic increase in luminosity and the clearing of the surrounding cocoon of gas and dust. The newborn star's radiation and stellar wind begin to clear away the surrounding gas and dust, revealing the star and illuminating the remaining nebula. The ultraviolet radiation from hot, massive stars ionizes the surrounding hydrogen, stripping electrons from atoms and causing the gas to glow with a characteristic red color, the signature of hydrogen emission. This creates what's called an emission nebula, a glowing cloud of ionized gas surrounding young stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is the nearest large emission nebula to Earth, about 1,350 light-years away, a stellar nursery where thousands of stars are currently forming. The Orion Nebula is illuminated primarily by 4 massive stars, called the trapezium, which emit enough ultraviolet radiation to ionize the surrounding gas for light-years in all directions. The most massive stars, those with tens of times the Sun's mass, burn through their fuel quickly, living only a few million years before exploding as supernovae. These massive stars have a profound effect on their surroundings. Their intense radiation and powerful stellar winds sculpt the nebula, carving out cavities and creating intricate structures. The radiation pressure pushes on dust grains, creating pillars and columns of dense gas that resist erosion. The famous pillars of creation in the Eagle Nebula are an example of this process, towering columns of gas and dust several light-years tall, sculpted by the radiation from nearby massive stars, with new stars forming in the densest parts of the pillars, protected from the erosive radiation by the surrounding material. When massive stars explode as supernovae, they release enormous amounts of energy and eject their outer layers into space at speeds of thousands of miles per second. This material, enriched with heavy elements created in the star's core and during the explosion itself, mixes with the surrounding interstellar medium, enriching it with elements heavier than hydrogen and helium. These heavy elements, carbon, nitrogen, oxygen, iron, and all the others, are essential for forming rocky planets and for life as we know it. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, was created in the core of a star and dispersed into space by a supernova explosion. We are, quite literally, made of stardust, assembled from atoms that were forged in stellar furnaces billions of years ago. The shock wave from a supernova can also trigger new star formation by compressing nearby clouds, creating a cycle where one generation of stars gives birth to the next. This process has been repeating for billions of years, with each generation of stars enriching the interstellar medium with heavier elements, gradually increasing the metallicity of the galaxy. The Sun and Solar System formed from a cloud that had been enriched by previous generations of stars, which is why Earth contains heavy elements and why life was able to evolve. The first stars in the universe, formed a few 100 million years after the Big Bang, contained only hydrogen and helium, and they could not have formed rocky planets or life as we know it. Not all nebulae are emission nebulae glowing with ionized gas. Reflection nebulae are clouds of dust that reflect the light of nearby stars, appearing blue because dust scatters blue light more efficiently than red light, the same reason Earth's sky is blue. The Pleiades star cluster is surrounded by a faint reflection nebula, visible in long-exposure photographs as blue wisps around the bright stars. Dark nebulae are dense clouds that block the light from stars behind them, appearing as dark patches against the background of stars or glowing nebulae. The Horsehead Nebula is a famous example, a dark cloud shaped like a horse's head silhouetted against a background emission nebula, sculpted by radiation from nearby stars into its distinctive shape. Planetary nebulae, despite their name, have nothing to do with planets. They're shells of gas ejected by dying stars, similar in mass to the Sun. When a Sun-like star exhausts the hydrogen in its core, it expands into a red giant, then sheds its outer layers in a series of pulses, creating a glowing shell of gas surrounding the hot, dense core that remains. This core, called a white dwarf, emits ultraviolet radiation that ionizes the ejected gas, causing it to glow in beautiful, often symmetric patterns. Planetary nebulae are short-lived, lasting only tens of thousands of years before the gas disperses into the interstellar medium. But during that brief time, they're among the most beautiful objects in the sky. The Ring Nebula and the Helix Nebula are famous examples, showing the intricate structures created as dying stars shed their outer layers. Supernova remnants are the expanding shells of gas and dust created by supernova explosions. These remnants can be hundreds of light years across and can remain visible for tens of thousands of years as they expand and interact with the surrounding interstellar medium. The Crab Nebula is a famous supernova remnant, the remains of a star that exploded in 1054 CE, observed and recorded by Chinese and Arab astronomers. At the center of the Crab Nebula is a pulsar, a rapidly rotating neutron star that emits beams of radiation like a cosmic lighthouse, spinning 30 times per second, the collapsed core of the star that exploded. The pulsar's energy drives the nebula's glow and creates intricate filamentary structures visible in detailed images. Moving beyond the glowing nebulae where stars are born, we drift into the vast emptiness between stars, into regions where darkness reigns and silence is absolute, where matter is so sparse that you could travel for light years without encountering anything larger than a dust grain. This interstellar space is not truly empty, but filled with an incredibly tenuous medium of gas and dust, magnetic fields, and cosmic rays, a near vacuum that nonetheless plays a crucial role in the galaxy's ecology. Tonight, we explore the interstellar silence, the beauty of the gaps between stars, and discover that, even in the emptiness, there is structure, chemistry, and a quiet grandeur that speaks to the vastness of the cosmos. The interstellar medium is the matter that exists between star systems in a galaxy, composed primarily of hydrogen gas, with about 10% helium and traces of heavier elements. The density of the interstellar medium is extraordinarily low, averaging about 1 atom per cubic centimeter in most regions, compared to about 10 to the 19th power atoms per cubic centimeter in Earth's atmosphere at sea level. This means that interstellar space is a better vacuum than anything we can create in laboratories on Earth. Yet despite this extreme tenuousness, the interstellar medium contains a significant fraction of the galaxy's mass, perhaps 10 to 15%, because the volume of space between stars is so vast. The interstellar medium is not uniform but exists in several distinct phases, with different temperatures and densities. The coldest and densest regions are molecular clouds, where temperatures drop to about 10 to 20 degrees above absolute zero, and densities can reach hundreds or thousands of atoms per cubic centimeter. These are the clouds where stars form, regions so cold that hydrogen atoms combine to form molecular hydrogen, and other molecules can form as well: carbon monoxide, water, ammonia, methanol, and even complex organic molecules containing dozens of atoms. More than 200 different molecules have been detected in interstellar space, including some that are important for life, suggesting that the chemistry necessary for life may be widespread in the universe. Among the most intriguing molecules detected in interstellar space are complex organic compounds that contain carbon chains and rings, the building blocks of biochemistry. Molecules like formaldehyde, ethanol, acetone, and even amino acids have been detected in molecular clouds, formed through chemical reactions on the surfaces of dust grains, or in the gas phase through ion molecule reactions. Some molecular clouds contain what astronomers call prebiotic molecules, compounds that could serve as precursors to the molecules of life. The discovery of these molecules suggests that the chemical pathways leading to life may begin in interstellar space, long before planets form, and that the ingredients for life may be delivered to new planetary systems by comets and asteroids that formed from the same molecular cloud as the planets. The warm, neutral medium is less dense, with about 0.5 atoms per cubic centimeter, and warmer, with temperatures around 6,000 to 10,000 degrees Fahrenheit. This is the most common phase of the interstellar medium, filling much of the space between molecular clouds. The hydrogen in this phase is mostly neutral, not ionized, and it emits radio waves at a wavelength of 21 centimeters, a characteristic emission that astronomers use to map the distribution of hydrogen throughout the galaxy. This 21 centimeter line was first detected in 1951 and has since become one of the most important tools for studying the structure and dynamics of galaxies. By mapping the 21 centimeter emission, astronomers can trace the spiral arms of the Milky Way, measure the rotation of the galaxy, and detect hydrogen in distant galaxies billions of light years away. The warm ionized medium has similar temperatures to the warm neutral medium, but lower densities, and the hydrogen is mostly ionized by ultraviolet radiation from hot stars. This phase fills the regions around hot stars and in the general interstellar space. The hot ionized medium is the hottest and most tenuous phase, with temperatures reaching millions of degrees Fahrenheit, but densities of only about 0.003 atoms per cubic centimeter. This phase is created by supernova explosions, which heat the surrounding gas to extreme temperatures, creating bubbles of hot gas that can be hundreds of light years across. Despite the high temperature, this gas doesn't feel hot because it's so tenuous. Temperature is a measure of the average kinetic energy of particles, but with so few particles, there's very little total energy. Our solar system resides within one of these hot bubbles, called the local bubble, a region of hot, low-density gas about 300 light-years across, created by supernova explosions over the past 10 to 20 million years. The local bubble is surrounded by a shell of denser, cooler gas, and beyond that lie other bubbles and clouds, creating a complex, frothy structure in the local interstellar medium. The Sun is currently moving through the local bubble at about 43,000 miles per hour relative to the local standard of rest, and in a few tens of thousands of years, it will exit the local bubble and enter a denser region of the interstellar medium, which could affect the heliosphere and potentially Earth's climate. Interstellar dust makes up only about 1% of the interstellar medium's mass, but it plays a crucial role in the chemistry and physics of space. Dust grains are tiny solid particles, typically about a micron across, composed of silicates, carbon, and ice, coated with organic molecules. These grains form in the atmospheres of cool stars and are ejected into space by stellar winds, or they condense from gas in supernova remnants. Dust grains absorb and scatter starlight, making distant stars appear dimmer and redder than they actually are, an effect called interstellar extinction. Dust also emits infrared radiation, glowing with the heat absorbed from starlight, and it provides surfaces where atoms can meet and combine to form molecules, catalyzing chemical reactions that would be difficult or impossible in the gas phase. The interstellar medium is threaded with magnetic fields, typically about 1,000,000 times weaker than Earth's magnetic field, but extending over vast distances, influencing the motion of charged particles and the formation of stars. These magnetic fields are created by the motion of ionized gas and are amplified by the rotation of the galaxy and by turbulent motions in the interstellar medium. Cosmic rays, high-energy particles traveling at nearly the speed of light, permeate the interstellar medium, created by supernova explosions and other energetic events. These cosmic rays ionize atoms in the interstellar medium, creating free electrons that interact with magnetic fields, and they can influence the chemistry of molecular clouds. The space between stars is not silent in the sense of having no activity. It's constantly being stirred by stellar winds, supernova explosions, and the rotation of the galaxy. Stellar winds from massive stars and from dying stars blow bubbles in the interstellar medium, sweeping up gas and creating shells of compressed material. Supernova explosions create shock waves that propagate through the interstellar medium for thousands of years, heating and compressing the gas, triggering new star formation, and mixing heavy elements into the medium. The galaxy's rotation creates spiral density waves, regions where the density of stars and gas is higher, and these waves compress the interstellar medium as they pass, triggering star formation in the spiral arms. The interstellar medium also participates in a galactic fountain, a cycle where gas is lifted from the galactic disk by supernova explosions and stellar winds, rises into the galactic halo, cools and condenses, and then falls back onto the disk. This fountain helps regulate star formation by removing gas from the disk and returning it later, enriched with heavy elements from supernovae. The fountain also helps maintain the vertical structure of the galactic disk, preventing all the gas from collapsing into a thin sheet. Yet despite all this activity, The interstellar medium is also a place of profound stillness. The distances are so vast, the densities so low, that interactions between particles are rare. A single atom in the warm neutral medium might travel for years before colliding with another atom. The timescales are immense. Molecular clouds can persist for millions of years before collapsing to form stars. Supernova remnants can expand for tens of thousands of years before merging with the general interstellar medium, and the galaxy's rotation takes about 250 million years to complete one orbit. This is a realm where patience is measured in eons, where change happens slowly, where the universe operates on timescales that dwarf human history. The interstellar medium is also a place of beauty, though not in ways visible to human eyes. If you could see in radio waves, you would see the 21-centimeter emission from neutral hydrogen, tracing the spiral arms of the galaxy, and the distribution of gas in the galactic disk. If you could see in infrared, you would see the glow of dust heated by starlight, revealing the locations of star-forming regions and the structure of molecular clouds. If you could see in X-rays, you would see the hot gas created by supernova explosions, glowing bubbles and shells marking the sites of stellar deaths. Each wavelength reveals a different aspect of the interstellar medium, a different layer of structure and activity. The chemistry of the interstellar medium is surprisingly rich. In the cold, dense cores of molecular clouds, where temperatures are only a few degrees above absolute zero, molecules can form on the surfaces of dust grains. Water ice, carbon monoxide, methane, ammonia, and more complex organic molecules accumulate on grain surfaces, creating icy mantles. When these grains are incorporated into forming stars and planets, they deliver these molecules to the new planetary systems, potentially seeding them with the ingredients for life. Some of the organic molecules detected in interstellar space are the same molecules found in living organisms on Earth, suggesting that the chemistry of life may have begun in interstellar space long before Earth formed. Pulling back our perspective from the spaces between individual stars, we now behold the galaxy itself, the Milky Way, a vast spiral of hundreds of billions of stars rotating slowly around a common center, a disk of light stretching across 100,000 light-years, so large that light takes 100,000 years to cross from one edge to the other. Our Sun is just one star among this multitude, orbiting the galactic center at a distance of about 26,000 light-years, completing one orbit every 225 to 250 million years, a galactic year. Tonight, we explore the galactic dance, the trillion-year rotation of the Milky Way, and discover that galaxies are not static collections of stars, but dynamic, evolving systems with structure, motion, and a history spanning billions of years. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure composed of stars, with spiral arms extending from the ends of the bar. The galaxy contains between 200 and 400 billion stars, though the exact number is uncertain because much of the galaxy is obscured by dust, and because many stars are too faint to detect individually. The total mass of the Milky Way is much greater than the mass of its stars, perhaps 1 trillion times the mass of the Sun, with most of this mass in the form of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, but reveals its presence through its gravitational effects. The galactic disk is where most of the galaxy's stars reside, a flattened structure about 1,000 light-years thick and 100,000 light-years in diameter. The disk contains young stars, old stars, gas, dust, and the spiral arms where star formation is most active. The spiral arms are not permanent structures, but density waves, regions where stars and gas are temporarily compressed as they orbit the galaxy. As material enters a spiral arm, it slows down due to the increased gravitational pull, creating a traffic jam of stars and gas. This compression triggers star formation, which is why spiral arms are bright. They contain many young, hot, luminous stars that illuminate the surrounding gas and dust. As stars leave the spiral arm, they speed up again, spreading out into the space between arms. Individual stars pass through spiral arms multiple times during their lifetimes, spending only a small fraction of their orbital period within the arms themselves. The Sun is located in a minor spiral arm called the Orion Arm, or local spur, situated between two major arms, the Perseus Arm and the Sagittarius Arm. The Sun orbits the galactic center at a speed of about 514,000 miles per hour. Though this seems slow on galactic scales, at this speed, the Sun takes 225 to 250 million years to complete one orbit, meaning that since the Sun formed 4.6 billion years ago, it has completed only about 20 orbits around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs were beginning to dominate Earth, and the continents were arranged differently than they are today. One galactic year ago, life on Earth consisted mostly of simple marine organisms, and the first plants were just beginning to colonize the land. At the center of the Milky Way lies a supermassive black hole called Sagittarius A, with a mass about 4 million times that of the Sun. This black hole is relatively quiet compared to the supermassive black holes in some other galaxies, not actively consuming large amounts of material, though it occasionally flares when gas or stars venture too close and are torn apart by tidal forces. The region around Sagittarius A is crowded with stars, with densities millions of times higher than in the solar neighborhood, and some of these stars orbit the black hole at tremendous speeds, completing orbits in just a few years. By tracking the orbits of these stars, astronomers have been able to measure the mass of the black hole with great precision and confirm that it's indeed a black hole, rather than some other massive object. One star, designated S2, orbits Sagittarius A every 16 years, reaching speeds of up to 3% the speed of light at its closest approach. Surrounding the galactic disk is the galactic bulge, a roughly spherical distribution of old stars extending several thousand light-years from the center. The bulge contains mostly old red stars, formed early in the galaxy's history, and it has a different chemical composition than the disk, with fewer heavy elements. The bar structure extends through the bulge, and the entire central region rotates as a unit, with stars orbiting in elongated paths aligned with the bar. The bar itself is thought to be a relatively recent feature, formed within the last few billion years through gravitational instabilities in the disk. Beyond the disk and bulge lies the galactic halo, a roughly spherical region extending perhaps 100,000 light-years or more from the galactic center. The halo contains old stars, globular clusters, and most of the galaxy's dark matter. Globular clusters are dense, spherical collections of hundreds of thousands to millions of stars, all formed at about the same time early in the galaxy's history. The Milky Way has about 150 known globular clusters, orbiting in the halo on highly elliptical paths that take them far from the galactic plane and then back through it. The stars in globular clusters are among the oldest in the galaxy, some nearly as old as the universe itself, about 13 billion years old. These ancient stellar populations provide a window into the early history of the galaxy and the universe. The dark matter halo is even larger, extending perhaps 600,000 light-years from the galactic center, containing most of the galaxy's mass. Dark matter doesn't interact with light, so we can't see it directly, but we can detect its gravitational effects. The rotation of the galaxy reveals the presence of dark matter. Stars in the outer parts of the galaxy orbit faster than they should based on the visible mass, indicating that there's additional mass we can't see. This dark matter holds the galaxy together, providing the gravitational glue that prevents stars from flying apart as the galaxy rotates. The Milky Way didn't form all at once, but assembled gradually over billions of years through the merger of smaller galaxies. Evidence for this comes from streams of stars in the halo that have similar compositions and motions, suggesting they were once part of smaller galaxies that were torn apart by the Milky Way's gravity. The Sagittarius dwarf elliptical galaxy is currently being consumed by the Milky Way, stretched into a stream that wraps around the galaxy multiple times. This process of galactic cannibalism continues today, with the Milky Way slowly absorbing its smaller satellite galaxies. The Milky Way has dozens of satellite galaxies, smaller galaxies that orbit it like moons orbit a planet. The largest are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as fuzzy patches of light. These irregular galaxies orbit the Milky Way at distances of about 160,000 and 200,000 light-years, respectively, and they're slowly being distorted by the Milky Way's gravity. The Magellanic Clouds are connected by a stream of gas called the Magellanic Stream, pulled out by tidal forces, stretching across more than 100 degrees of the sky. The galaxy's stellar populations tell the story of its evolution. Population I stars, found primarily in the disk and spiral arms, are relatively young and metal-rich, formed from gas that has been enriched by previous generations of stars. These stars include the Sun and most of the stars visible to the naked eye. Population II stars, found primarily in the halo and globular clusters, are old and metal-poor, formed early in the galaxy's history when the interstellar medium contained mostly hydrogen and helium. The chemical composition of stars serves as a fossil record of the galaxy's enrichment history, with each generation of stars incorporating more heavy elements than the previous generation. The Milky Way is part of a larger structure called the Local Group, a collection of more than 50 galaxies bound together by gravity. The two largest members are the Milky Way and the Andromeda Galaxy, a spiral galaxy about 2.5 million light-years away. Andromeda is slightly larger than the Milky Way, containing perhaps 1 trillion stars, and it's moving toward us at about 250,000 miles per hour. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge, creating a giant elliptical galaxy that astronomers have nicknamed Milkomeda. This collision won't be catastrophic for individual stars. The distances between stars are so vast that direct collisions between stars will be extremely rare, but the galaxy's structures will be disrupted, and the merger will trigger intense star formation as gas clouds collide and compress. The rotation of the Milky Way is not uniform. Different parts rotate at different speeds. Near the galactic center, stars orbit quickly due to the strong gravitational pull of the central mass. Farther out, in the disk where the Sun orbits, the rotation speed is roughly constant, about 140 miles per second, which is why the rotation period is about 225 million years. This differential rotation means that the galaxy doesn't rotate like a solid disk, but more like a fluid, with inner parts completing orbits faster than outer parts. This differential rotation winds up the spiral arms, though the arms themselves are density waves that rotate at a different speed than the stars. The Milky Way is also moving through space as part of larger structures. The local group is falling toward the Virgo cluster, a large collection of galaxies about 50 million light-years away. And the Virgo cluster is itself part of an even larger structure called the Laniakea supercluster, a collection of galaxy clusters spanning 520 million light-years. All of these structures are moving in response to the gravitational pull of mass concentrations and the expansion of the universe, creating a cosmic flow that carries galaxies through space, expanding our view beyond the Milky Way, beyond the local group, beyond even the nearby clusters and superclusters. We venture into the deep universe, into regions so distant that the light reaching us today began its journey billions of years ago, when the universe was young, when the first galaxies were just beginning to form. These distant galaxies appear not as they are now, but as they were in the ancient past, their light traveling across billions of light-years of expanding space to reach our telescopes. Tonight we explore the deep field, galaxies from the dawn of time, and discover that looking into deep space is looking back in time, that the universe has a history, an evolution, a story written in the light of distant galaxies. The Hubble Deep Field, an image captured by the Hubble Space Telescope in 1995, revolutionized our understanding of the distant universe. Astronomers pointed the telescope at a tiny, apparently empty patch of sky, about the size of a grain of sand held at arm's length, and exposed the camera for 10 days, collecting every photon of light from that region. The resulting image revealed not emptiness, but thousands of galaxies, each containing billions of stars, stretching back to within a billion years of the Big Bang. This single image demonstrated that the universe is filled with galaxies, that even the apparently empty spaces between nearby stars contain countless distant galaxies, and that we can observe the universe's history by looking at galaxies at different distances. Light travels at a finite speed, about 186,000 miles per second, which means that when we look at distant objects, we see them not as they are now, but as they were when the light left them. When we look at the sun, we see it as it was 8 minutes ago. When we look at the nearest star beyond the sun, Proxima Centauri, we see it as it was 4.2 years ago. When we look at the Andromeda Galaxy, we see it as it was 2.5 million years ago. And when we look at the most distant galaxies visible in deep field images, we see them as they were more than 13 billion years ago, less than a billion years after the Big Bang, when the universe was only about 5% of its current age. The universe began about 13.8 billion years ago in the Big Bang, an event that created space, time, matter, and energy. In the first moments after the Big Bang, the universe was incredibly hot and dense, filled with a soup of fundamental particles. As the universe expanded and cooled, these particles combined to form protons, neutrons, and electrons, and eventually the first atoms, mostly hydrogen and helium. For about 380,000 years, the universe was opaque, filled with a hot plasma that scattered light. But when the universe cooled enough for electrons to combine with protons to form neutral atoms, the universe became transparent, and light could travel freely through space. This light, stretched to microwave wavelengths by the expansion of the universe, is still visible today as the cosmic microwave background, the afterglow of the Big Bang. After the universe became transparent, it entered a period called the Dark Ages, when there were no stars or galaxies, only neutral hydrogen gas filling space. Gravity began to pull this gas into denser regions, creating the seeds of the first structures. About 100 to 200 million years after the Big Bang, the first stars formed, massive stars that lived fast and died young, exploding as supernovae and enriching the surrounding gas with heavy elements. These first stars were different from stars today. They contained no heavy elements, only hydrogen and helium, and they were probably much more massive than typical stars, perhaps hundreds of times the mass of the Sun. The first galaxies formed shortly after the first stars, as gravity pulled together millions or billions of stars into bound systems. These early galaxies were smaller and more irregular than galaxies today, and they grew through mergers, with smaller galaxies colliding and combining to form larger ones. This hierarchical assembly process continues today, with galaxies still merging and growing, though the rate of mergers has decreased as the universe has expanded and galaxies have become more spread out. The Hubble ultra-deep field, an even deeper image, captured in 2004, revealed galaxies from even earlier times, some from less than 500 million years after the Big Bang. These galaxies appear small, irregular, and blue, indicating that they contain many young, hot stars and are actively forming new stars. The galaxies are also clumpy and chaotic, lacking the organized spiral or elliptical structures of nearby galaxies, suggesting that galaxy morphology evolves over time as galaxies merge and settle into more stable configurations. The James Webb Space Telescope, launched in 2200, has pushed even deeper into the early universe, observing galaxies from as early as 300 million years after the Big Bang. These observations have revealed that galaxies formed earlier and evolved faster than previously thought, with some early galaxies already containing billions of stars and showing signs of organized structure. The early universe was a more active and dynamic place than astronomers expected, with rapid star formation, frequent mergers, and the quick assembly of massive galaxies. Among the most luminous objects in the distant universe are quasars, extremely bright galactic nuclei, powered by supermassive black holes actively consuming matter. Quasars can outshine entire galaxies, emitting as much energy as 1 trillion suns from a region smaller than our solar system. They were most common when the universe was about 2 to 3 billion years old, during the peak era of galaxy formation and black hole growth. The light from the most distant quasars has been traveling for more than 13 billion years, showing us what these objects looked like when the universe was less than 1 billion years old. Quasars serve as beacons that illuminate the early universe, and their light, passing through intervening gas clouds, reveals the distribution and composition of matter between us and the quasar. Gravitational lensing provides another window into the distant universe. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravity of the intervening mass bends the light, magnifying and distorting the image of the background galaxy. This natural telescope effect allows astronomers to observe galaxies that would otherwise be too faint to detect, revealing details of the early universe that would be invisible without the magnification. Some gravitational lenses create multiple images of the same background galaxy, or stretch it into arcs and rings, creating beautiful and scientifically valuable patterns. Galaxies come in several main types, classified by their appearance. Spiral galaxies, like the Milky Way and Andromeda, have rotating disks with spiral arms and central bulges. They're actively forming stars in their disks and contain significant amounts of gas and dust. Elliptical galaxies are smooth, featureless, and elliptical in shape, ranging from nearly spherical to highly elongated. They contain mostly old stars, little gas or dust, and little ongoing star formation. Elliptical galaxies are thought to form primarily through mergers of spiral galaxies, which disrupt the disk structures and trigger intense star formation that consumes most of the available gas. Irregular galaxies lack organized structure and are often small and chaotic, sometimes the result of gravitational interactions or mergers. The distribution of galaxy types has changed over cosmic time. In the early universe, most galaxies were small, irregular, and actively forming stars. Over billions of years, these galaxies merged to form larger galaxies, and many evolved into spiral or elliptical galaxies. The rate of star formation in the universe peaked about 10 billion years ago and has been declining since, as galaxies have consumed or expelled much of their gas, and as the expansion of the universe has made it harder for galaxies to acquire new gas from their surroundings. This cosmic downturn in star formation means that most stars in the universe have already been born, and future star formation will be increasingly rare. Measuring distances to galaxies is one of the fundamental challenges in astronomy. For nearby galaxies, astronomers use standard candles, objects of known intrinsic brightness, to measure distance. By comparing the known brightness to the observed brightness, they can calculate how far away the object must be. Cepheid variable stars, which pulsate with periods related to their intrinsic brightness, serve as excellent standard candles for galaxies within about 100 million light-years. For more distant galaxies, astronomers use Type Ai supernovae, exploding white dwarf stars that have remarkably consistent peak brightness, allowing distance measurements out to billions of light-years. This cosmic distance ladder, built from overlapping distance measurement techniques, allows astronomers to map the universe and measure its expansion. Galaxies are not isolated, but exist in a cosmic web of structure, with galaxies clustered along filaments and sheets surrounding vast voids. This large-scale structure formed through gravitational instability, with denser regions attracting more matter and becoming denser still, while less dense regions lost matter and became emptier. The cosmic web is visible in galaxy surveys that map the three-dimensional distribution of galaxies across large volumes of space, revealing a foam-like structure with galaxies concentrated in filaments and clusters and voids containing few galaxies. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies bound together by gravity. The space between galaxies in clusters is filled with hot gas, heated to millions of degrees by the gravitational energy of the cluster, and this gas emits X-rays that can be detected by X-ray telescopes. Galaxy clusters also contain large amounts of dark matter, which provides most of the gravitational mass holding the cluster together. By studying the motions of galaxies in clusters and the distribution of hot gas, astronomers can measure the total mass of clusters and infer the amount of dark matter. We have journeyed from our sun to the edge of the observable universe, from the familiar warmth of our star to the most distant galaxies visible in the deepest images. And now, in this final chapter, we step back to contemplate the universe as a whole, the vast expanding cosmos that contains all the stars, galaxies, and structures we have explored. The universe is not static but dynamic, expanding in all directions, carrying galaxies away from each other, stretching space itself. Tonight we explore the expanding universe, the cosmic lullaby that has been playing for 13.8 billion years, and discover that the universe has a past, a present, and a future, a grand arc of cosmic evolution that encompasses everything that exists. The expansion of the universe was discovered in the 1920s by Edwin Hubble, who observed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, now called Hubble's law, revealed that the universe is expanding uniformly in all directions, with the space between galaxies stretching over time. This expansion doesn't mean that galaxies are moving through space away from a central point, but rather that space itself is expanding, carrying galaxies along with it. Every point in the universe sees every other point receding, and there is no center to the expansion. From any galaxy's perspective, all other galaxies appear to be moving away. The discovery of the universe's expansion led to the realization that the universe must have been smaller and denser in the past. Extrapolating backward in time, astronomers concluded that the universe began in an extremely hot, dense state about 13.8 billion years ago, an event we call the Big Bang. The Big Bang was not an explosion in space, but an expansion of space itself, creating space, time, matter, and energy simultaneously. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation, growing from smaller than an atom to macroscopic size in an instant, smoothing out irregularities and setting the initial conditions for all subsequent cosmic evolution. As the universe expanded, it cooled. In the first seconds, it was hot enough for nuclear reactions to occur, fusing hydrogen into helium and traces of other light elements. This process, called Big Bang nucleosynthesis, created the primordial abundances of elements that we still observe today. About 75% hydrogen and 25% helium by mass, with tiny traces of lithium and other light elements. All heavier elements were created later in stars and dispersed by supernova explosions, but the hydrogen and helium that make up most of the universe's ordinary matter were created in the first few minutes after the Big Bang. For the first 380,000 years, the universe was opaque, filled with a hot plasma of electrons and protons that scattered light. But as the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, and the universe became transparent. The light from this moment, stretched by billions of years of cosmic expansion, is still visible today as the cosmic microwave background, a faint glow of microwave radiation coming from all directions in the sky. This radiation, discovered accidentally in 1965, is the oldest light in the universe, a snapshot of the cosmos when it was only 380,000 years old, and it provides crucial information about the early universe's temperature, density, and composition. The cosmic microwave background is remarkably uniform, with a temperature of about 2.7 degrees above absolute zero in all directions, but it contains tiny variations, about 1 part in 100,000, that represent the seeds of all cosmic structure. These tiny density fluctuations created by quantum fluctuations during inflation and amplified by cosmic expansion were the regions where gravity would eventually pull matter together to form the first stars, galaxies, and galaxy clusters. By mapping these fluctuations with exquisite precision, astronomers have been able to determine the universe's age, composition, and geometry with unprecedented accuracy. The cosmic microwave background tells us that the universe is flat, meaning that parallel lines remain parallel forever, that the universe will expand forever, and that the total energy density of the universe is precisely balanced at the critical value separating eternal expansion from eventual collapse. The universe is composed of several components with very different properties. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for only about 5% of the universe's total energy content. Dark matter, which doesn't emit, absorb, or reflect light, but reveals its presence through gravitational effects, accounts for about 27%. The remaining 68% is dark energy, a mysterious component that causes the expansion of the universe to accelerate. Dark energy was discovered in 1998 when astronomers studying distant supernovae found that the universe's expansion is speeding up rather than slowing down as expected. The nature of dark energy remains one of the biggest mysteries in physics. It behaves like a property of space itself, with constant density even as the universe expands, pushing galaxies apart with ever-increasing strength. The accelerating expansion driven by dark energy has profound implications for the universe's future. In the distant future, billions of years from now, the expansion will carry distant galaxies beyond the observable universe, their light redshifted to such long wavelengths that it becomes undetectable. Eventually, only the galaxies in our local group will remain visible, bound together by gravity and resisting the cosmic expansion. All other galaxies will have receded beyond the cosmic horizon, their light unable to reach us across the expanding space. The universe will become a lonelier place, with each gravitationally bound group of galaxies isolated in an expanding void. Before that distant future arrives, our own solar system will undergo dramatic changes. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. This will cause the Sun to expand into a red giant, growing so large that it will engulf Mercury and Venus, and possibly Earth. The Sun's outer layers will extend beyond Earth's current orbit, though Earth itself may spiral outward as the Sun loses mass. Even if Earth survives, it will be a scorched, lifeless world, its oceans boiled away, its atmosphere stripped, its surface molten. After about 1 billion years as a red giant, the Sun will shed its outer layers, creating a planetary nebula, and the core will collapse into a white dwarf, a dense stellar remnant about the size of Earth, but containing about half the Sun's current mass. This white dwarf will slowly cool over trillions of years, eventually becoming a cold, dark black dwarf. On even longer timescales, trillions of years in the future, star formation will cease as galaxies exhaust their supplies of gas. The stars that exist will gradually burn out, with the longest-lived red dwarf stars shining for trillions of years before finally fading. Eventually, the universe will contain only stellar remnants, white dwarfs, neutron stars, and black holes, along with planets, asteroids, and the diffuse gas that was never incorporated into stars. This era, called the degenerate era, will last for an incomprehensibly long time, with the universe growing ever darker and colder as the last remnants of stellar light fade away. On timescales of 10 to the 40th power years or longer, even these remnants will decay or evaporate. Protons may decay into lighter particles, causing white dwarfs and neutron stars to gradually disintegrate. Black holes will evaporate through Hawking radiation, a quantum process that causes black holes to slowly lose mass and eventually disappear in a final burst of radiation. The timescale for this process is staggeringly long. A black hole with the mass of the Sun would take 10 to the 67th power years to evaporate, and supermassive black holes would take even longer. But given enough time, even black holes will vanish, leaving the universe in a state of maximum entropy, a cold, dark, nearly empty expanse approaching absolute zero. Yet despite this distant future of heat death, the universe we inhabit now is vibrant and alive with activity. Stars are being born in nebulae, galaxies are colliding and merging, black holes are consuming matter and powering quasars, and planets are forming around young stars. We live in a special epoch, billions of years after the Big Bang, but trillions of years before the last stars fade, in a universe that is neither too young nor too old, a universe that has had time to form complex structures, but still has abundant energy and activity. We live in what might be called the stelliferous era, the age of stars, when the universe is illuminated by the light of countless suns, when galaxies shine brightly, when life can emerge and evolve on planets orbiting stable stars. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is about 93 billion light-years in diameter. This is larger than 13.8 billion light-years because the universe has been expanding while the light has been traveling, stretching the distance between us and the sources of the most distant light. The observable universe contains at least 2 trillion galaxies, each with billions or trillions of stars, and countless planets, moons, asteroids, and comets. The total number of stars in the observable universe is estimated to be about 10 to the 24th power, a number so large it exceeds the number of grains of sand on all of Earth's beaches. And so tonight, as you rest, as you prepare to drift into sleep, imagine the universe expanding around you, space itself stretching, carrying distant galaxies away while the local group remains bound together by gravity. Imagine the cosmic microwave background, the ancient light from the early universe passing through your location right now, photons that have been traveling for 13.8 billion years, carrying information about the universe's birth. Imagine the dark energy permeating all of space, gently pushing the universe to expand faster and faster, shaping the cosmos's ultimate fate. You are part of this expanding universe, made of atoms forged in stars, living on a planet orbiting a star in a galaxy that is itself part of a vast cosmic web of structure. Let that awareness settle over you now. Let the knowledge that the universe is vast beyond comprehension, ancient beyond imagining, yet knowable through observation and reason. Let that bring you peace. The universe will continue its expansion while you sleep, will continue its slow evolution from the hot, dense state of the Big Bang toward the cold, dark future of heat death. But that future is trillions of years away, and for now the universe is filled with light and life and wonder. Rest now in the cosmic lullaby, in the gentle expansion of space, in the knowledge that you are a part of the universe experiencing itself, a way for the cosmos to know itself. Sleep now, and let the expanding universe carry you gently into dreams, into the deep sleep of space, into the peaceful awareness that you are home, here, now, in this vast and beautiful cosmos. Sleep now. The universe will keep expanding, the stars will keep shining, and the cosmic story will continue while you rest.